Hi everybody, once again it's Mr. Spudik, and today we are going to talk about conservation of energy. This is part 2 of our lesson and lecture on energy. If you haven't watched the previous video on work and simple machines, I suggest you go back to that first, okay, because you really want to understand work before you move into conservation of energy. Okay, moving into it, let's talk about it. There are many different ways or different types of energy, okay? We have potential energy, we have kinetic energy, we have heat. Heat is a type of energy. We're going to talk about potential and kinetic energies today, and we might talk a little bit about how you can lose or gain energy from heat. What I said before in the previous lecture, I'm going to remind you about, this is really tied in with your history lesson. Okay, when you hear about the steam engine and the Industrial Revolution, what happened was this. It was a way to get energy or work done from energy. So what James Watt and other scientists were able to figure out was that if they took so much heat and they could somehow get that heat to do a job, it replaced workers, all right? It replaced other people to do it for them. And it was the idea that we could now use heat. We could use fire and heat to transfer that into work being done. And that's the whole idea of conservation of energy, which is what we're learning today. All right, so we are going to talk about potential energy. Potential energy is when something has potential to it, whether it be something being lifted up high or something that's pushed in like a spring. Those are a couple of ways that you could have potential energy. Kinetic energy would be, say, when something's moving. We're going to talk about just regular linear kinetic energy, but also even when something's spinning. Okay, if something's spinning and it's not moving along, that is a type of kinetic energy too. All right, but the basic idea let's talk about first is you have potential and kinetic. Okay, gravitational potential energy. That's our normal potential energy, which is what you probably learned about before. So gravitational potential energy is that if something is at a certain height, it will have a certain amount of potential energy because it has the potential to fall. Okay? Our formula for potential energy, your teacher might give you the letter U, okay, or PE. It depends on the textbook, really. Some people will use the letter U because that really stands truly for gravitational potential energy in most textbooks. But I get lazy, I really do, and I will write just PE a lot of times. But the formula is going to be potential energy is equal to mass times gravity times height. The units for potential energy are joules, named after another scientist that was working on this conservation of energy. Okay, so let's do a quick calculation. Let's see how we do. If I have 3 kilogram book, and I'm holding it up 1.2 meters, how many joules of potential energy does it have? I'll wait and let you calculate it. 3 kilograms, 1.2 meters. If you got an answer of 3.6, you're wrong. Don't forget about gravity, okay? And that could be a common mistake that some of our students are going to make. Do not forget that you have G, which is 9.8, plugged into that. So the answer really should be 35.28 joules of potential energy. Okay? All right, now, kinetic energy. Kinetic energy, you could see the letter K or KE. See, I already got lazy here, okay, and just did KE instead of K. The formula for kinetic energy when something's moving along in a straight line is going to be 1/2 mv squared. 1/2 the mass times the velocity squared. Now, what do you think the units are going to be for that? Well, the units have to be the same as potential energy, so they will transfer back and forth. So the units for kinetic energy and potential energy have to be the same. They are still joules. Okay, if you think about it as apples and oranges, right? You can't pass those back and forth. If we're passing joules, they have to be, or if potential and kinetic energy, if they have different units, they can't be transferred back and forth. Okay, So there is the quick and easy calculation for, or formula for, kinetic energy. All right, now, all that is well and good. As a teacher, I could give you a question on a test. What is the potential energy of this if it's lifted to a certain height? What is the kinetic energy of this if it's going this velocity? But really, that's not the key. The key is this whole idea of conservation of energy, that energy will be transferred back and forth. Okay? And this is where it's really helpful. All right? So you could have energy if I lift something up. We talked about work before. So if I did work to lift something up, well, that the work I did will transfer to the potential energy I gained. Okay? If I'm trying to stop something even, I'm going to do force times distance to try to stop something. Okay? The force times the distance that I have to push to slow something down. Let's say I'm Superman slowing down a train to stop it. Well, the force times the distance of friction or whatever else to fight to slow down that train will be equal to the kinetic energy that the train had. Okay? Your police, there are people in the police department that work with this conservation of energy all the time. And there's been times where they'll come in and talk to students and talk about their formulas. And what you would find out is this. Let's say they go to a scene of an accident and they see a skid mark on the road and a car sitting over on one spot and another car had collided in. What they can do is they can measure the distance of the skid mark, okay? And that would be a distance that there is friction being applied. So you have a force times the distance, okay, being applied, the force of friction times the distance that car traveled, okay? And that would be equal to the kinetic energy that it was hit with previously. So they could work their way back in a scene and figure out how fast another car was traveling to hit the car just by using conservation of energy and a little bit of conservation of momentum that you might have learned about previously. Okay? So conservation of energy is huge. And there's a lot of ways that you have to figure out, okay, how much energy did I have before? How much energy do I have after? And you'll solve for a missing variable. Okay, so here's a very, very basic plan for it. Let's say that I have a box at the top of a ramp. And let's say the ramp, let's not even worry about the height or worry about the mass. Let's just say that I know that the energy that this box has at the top of the ramp, the potential energy is 10 joules. Okay? Let's say it's sitting still. So if it's sitting still and the velocity is 0, how much kinetic energy do you think it has? There will be 0 joules of kinetic energy at the top because it's not moving. Now, let's say this box, instead of going down the ramp the first time, it falls straight down. Okay, so it's going to fall straight down here. All right. Well, as it falls, it's going to lose height. And if you have height in your potential energy formula, that means as it falls, it's going to lose potential energy. So halfway down, let's say halfway down the ramp, if it has half the height, okay, or halfway down the fall, if it has half the height, it's going to have half the potential energy. So here, my potential energy will only be 5 joules. Well, how much energy kinetic must it have? Okay, the conservation of energy says that the total energy before has to be equal to the total energy after. Before, we had 10 joules of potential plus 0 joules of kinetic. So our total was 10. All right? So, halfway down, if I now have only 5 joules of potential, that means I must have 5 joules of kinetic as well, so that they still add up to 10. All right, now, what about a point D? Let's say right here, right before the box hits the ground. Don't assume, oh, the box hit the ground, there's no more joules. Okay? Right before that box hits the ground, how much potential energy do you think something has if there is no height to it? It just is about to hit the ground. Potential energy is going to be 0, right? So, how many joules of kinetic must it have? Well, again, the total before has to be equal to the total after. So I need to have 10 joules of kinetic if energy has to be conserved. Okay, now, what about sliding down a ramp? So let's say this time, instead of falling straight down, it slid down the ramp. Well, let's assume that point C is the same height as point B. It has to be the same with the energies as well. Because again, if point C is the same height as point B, it's down half the height, potential energy U is still going to be 5 joules right here. And that means the kinetic energy has to be 5 as well. All right, at the bottom, once it's gone off the ramp and it's sliding along, it's going in a different direction than this box was when it was going down just before it hit. But it doesn't matter. The path does not matter. Down here, the potential energy is going to be 0 joules. That means the kinetic has to be 10 joules. Okay, so again, the whole idea with conservation of energy is the total energy before is equal to the total energy after. Okay? Now, we didn't talk about heat, but that could be a part. If something is going to collide with something else, you could, obviously if I drop this box, it did stop. Okay? If it stopped, where did all that kinetic energy go? Well, it got lost to heat. Okay? So heat is being put in here too. We won't do as much calculations with heat in our practice problems, but understand that you can lose energy to heat. Okay? All right. One little example, and then I'm going to let you go. Let's say that I have a skier, and that skier is moving at the top of the hill right before she goes down the hill. Okay? So let's say that she is moving. If she is moving and she's at the top of the hill, what type of energies does she have? She's going to have kinetic energy because she's moving, and because she's at the top of the hill, she has potential. What you would do for this is, let's say I want to know how fast she'll be going at the bottom. Okay? I would list all my energies beforehand and all my energies after. Okay? I would put everything before on the left, everything after on the right. So let's list out what we have here. Okay? So I'm going to write before and after. All right, let's think about it. Again, I said that we have potential energy because she's at the top of the hill. All right? And she has kinetic because she's moving. All right, so we have a height here. Now, after, when she's at the bottom of the hill, if she's at the bottom of the hill and the height is 0, does she have potential energy? No. She has kinetic only. So she'll have kinetic here. Now, the numbers are going to be different, so I'll put a little 1 here, and I'll put a little 2 there. Okay? So the first step when you do conservation of energy problems is just list all the energies before on the left-hand side, list all the energies after on the right-hand side. After that, you would substitute in the equations. So the formula for potential energy is mgh. Formula for kinetic energy is 1/2 mv squared. And I'm going to put a 1 here again to make sure we say it's not the same velocity as after. All right. Now, after we only have kinetic. So we have a 1/2 mv squared again, and I'll put a 2 there. All right. From that point, you could do your algebra. And I'm going to let you do the algebra later. Okay. But I want to point something out. You might not be given mass in this problem. And you're going to say, but Mr. Spudik, we need mass. Mass is in 3 times. But I want you to notice something. Mass is put in 3 times. And if you did any math to factor these masses out, they would all get canceled out. Okay? So sometimes you might not be given mass and you think you do need it. But it's because they will cancel out. All right. That is it for me. Thanks so much for watching, and I'll see you next time.